Somewhere beyond Neptune, farther from the Sun than any probe has ever travelled, there may be a world we have never seen. It has no photograph. It casts no visible shadow. No telescope has ever caught its light, and no spacecraft has ever felt its pull. And yet, in the quiet mathematics of orbital mechanics, something is there. Something massive. Something patient. Something that has been shaping the outermost reaches of our solar system for longer than human beings have existed, bending the paths of distant ice worlds with an invisible hand. Tonight, we're going to talk about Planet 9, the world that exists only in equations, the gravitational ghost that we can measure but cannot find, the largest object in our cosmic neighbourhood that may have been hiding from us for 4.5 billion years. It is a mystery that lives at the very edge of what we know, in that strange territory where physics becomes poetry, and the boundaries of our solar system blur into the darkness between stars. What is out there? A frozen super-Earth, born in the early chaos of planetary formation and flung into exile. A wandering world from some other star system captured by our sun's gravity as it drifted through the galaxy. Or something stranger still. Something so bizarre that the very idea of it feels like science fiction, yet rests on mathematics as sound as any in physics. By the end of tonight, you're going to understand exactly why so many astronomers believe something massive is orbiting in the outer darkness, why we still cannot see it, and why the true identity of Planet 9 might be far stranger than anyone first imagined. The answer is not simple, and it is not settled. But the journey to find it will take us to the very limits of observation, to the earliest moments of the solar system's birth, and to a hypothesis so unsettling that it was first proposed almost as a thought experiment, only to be taken seriously by some of the finest minds in astrophysics. Before we get started, if you love exploring the mysteries of our universe as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The story of Planet 9 does not start with a discovery. It starts with a pattern, a strange alignment of orbits that no one could explain. To understand it, we need to travel outward, past the familiar planets, past the asteroid belt, past the ice giants Uranus and Neptune, out into a region of the solar system so distant and so dark that it was not even theorized to exist until the middle of the 20th century. This is the Kuiper Belt, a vast ring of frozen worlds that circles the Sun beyond Neptune's orbit. When astronomers first began discovering objects there in the early 1990s, they expected to find a fairly random distribution of icy bodies, the leftover debris from the solar system's formation scattered more or less evenly around the Sun. And for the most part, that is what they found. Thousands upon thousands of small frozen worlds, tumbling through the darkness in orbits that seemed to follow no particular pattern. But then, as the decades passed and telescopes grew more powerful, a handful of extremely distant objects began to reveal themselves. These were not like the ordinary Kuiper Belt residents. They were farther out, their orbits stretching into regions of space so remote that even sunlight takes hours to reach them. And they were doing something peculiar. Their orbits were aligned. Imagine dropping a handful of pebbles into a pond and watching them drift. You would expect them to spread out in all directions, each following its own random path. But these distant objects, these trans-Neptunian bodies with orbits that take thousands of years to complete, were not behaving randomly at all. Their elongated paths through space, their orbital ellipses were clustered together, pointing in roughly the same direction as if guided by an invisible shepherd. The first astronomer to notice this pattern was Chad Trucchio, working alongside his colleague Scott Shepherd at the Carnegie Institution for Science. In 2013, they discovered a new object called 2012 VP1013, one of the most distant bodies ever found in our solar system. When they compared its orbit to Sedna, another extremely distant world discovered a decade earlier, they noticed something strange. Both objects had orbits that were remarkably similar in orientation. Both were being pulled in the same direction, as if responding to a gravitational influence that no one had accounted for. They published their findings quietly, noting the alignment but not yet proposing a cause. It was an observation, a curiosity, a thread hanging loose at the edge of our understanding. But it caught the attention of two scientists at the California Institute of Technology, two men who would spend the next several years pulling on that thread until it unravelled into something extraordinary. Their names were Konstantin Batygin and Mike Brown, and in the winter of 2016, they announced a hypothesis that would reshape our understanding of the solar system. Brown, already famous in planetary science circles as the man who had effectively demoted Pluto from planetary status, had spent years cataloguing distant objects in the outer solar system. Batygin, a theoretical astrophysicist with a gift for computational modelling, had the mathematical tools to test whether the strange orbital alignments could be explained by chance, or whether something else was required. Together they built simulations. They fed the known orbits of distant trans-Neptunian objects into computer models and asked a simple question. What are the odds that these alignments happened randomly? The answer was startling. Less than 1%, perhaps as low as 1 in 10,000. The clustering was real, and it was almost certainly not an accident. But if not chance, then what? The most elegant explanation, the one that fit the mathematics most cleanly, was gravity. Something out there, something with significant mass, was shepherding these distant objects into their aligned orbits. Something was pulling on them, gently but persistently, over millions and billions of years. And when Batygin and Brown worked backward from the orbits to calculate what kind of object could produce such an effect, the answer was unmistakable. A planet, not a small one either. Their model suggested a world roughly 10 times the mass of Earth, orbiting the Sun at an average distance of perhaps 400 to 800 astronomical units. That is, 400 to 800 times the distance from Earth to the Sun. At that distance, even an object many times the size of our own world would be almost impossibly faint, reflecting so little sunlight that it would be lost in the background noise of stars and galaxies. This was Planet 9, or rather, this was the mathematical signature of Planet 9. The equation said it should exist. The orbital alignments demanded an explanation, but no one had ever seen it. No telescope had captured its image. It was and remains a world defined entirely by its absence, a gravitational shadow cast across the outer solar system, visible only in the paths of the objects it has bent. Let us pause for a moment and consider what it means to know something exists without ever having seen it. In science, this is not unusual. For decades, astronomers knew that dark matter must exist because of the way galaxies rotate, even though no one had ever detected a particle of it directly. Neptune itself was predicted mathematically, before anyone pointed a telescope at the right patch of sky. The history of astronomy is full of invisible things made visible only by their effects on the things around them. But Planet 9 is different. Neptune was found within months of its prediction. Dark matter, though unseen, has been confirmed by countless independent observations. Planet 9 has been sought for nearly a decade now, and still it hides. Part of the problem is simply distance. If Planet 9 orbits at the distances Batygin and Brown predict, it would be the most remote major object in our solar system, farther from the Sun than any planet has ever been found. At 600 astronomical units, a figure in the middle of the predicted range, sunlight would take more than 3 days to reach it. The light it reflected back would be so feeble that even the most powerful telescopes on Earth would struggle to distinguish it from the countless faint background objects that litter every image of the sky. And the search area is vast. The outer solar system is not a place with clear boundaries. It fades gradually into the interstellar medium, the space between stars, with no signpost marking where our neighbourhood ends and the rest of the galaxy begins. Searching for Planet 9 is like looking for a single grain of sand on a beach that stretches to the horizon in every direction, except the grain of sand is moving slowly but constantly, along an orbit that takes perhaps 10,000 years to complete. Astronomers have tried. The Subaru telescope in Hawaii, with its wide field of view and exceptional sensitivity, has been particularly useful, scanning swathes of sky night after night in search of a slowly moving point of light that might betray a distant world. Other observatories have contributed their own searches, but the sky is large, and Planet 9, if it exists, is small, cold, and dark. Yet the mathematical case has only grown stronger with time. New distant objects have been discovered, and most of them fit the predicted pattern. Their orbits cluster in ways that continue to demand explanation. Some astronomers have raised alternative hypotheses. Perhaps the clustering is an observational bias, a trick of the way we search for distant objects. But Batygin and Brown have tested these alternatives and found them wanting. The simulations still point toward a massive, unseen world, and so we're left with a profound uncertainty. a kind of cosmic suspense that has stretched for years without resolution. Somewhere out there, either there is a planet, a real, physical world of rock and ice and frozen atmosphere, larger than Earth, older than human civilization, quietly orbiting the sun in perfect darkness, or there is not. And either answer carries extraordinary implications. But here is where the story takes a turn that even Bettigen and Brown did not anticipate. Because in the years since their original paper, other scientists have begun to ask a different question. Not whether Planet 9 exists, but what it might actually be. The default assumption, the most conservative hypothesis, is that Planet 9 is exactly what its name suggests. A planet. A super-Earth, perhaps, or a mini-Neptune. One of those intermediate-sized worlds that seem to be common around other stars, but that we have never confirmed in our own solar system. Such a world would have formed in the early solar system, probably much closer to the Sun, before gravitational interactions with the giant planets flung it outward into its current distant orbit. It would be a frozen world now, its surface locked in temperatures barely above absolute zero, its atmosphere, if it ever had one, long since condensed into ices on its surface. This is a strange scenario, but not an impossible one. Simulations of the early solar system suggest that such ejections were common. Jupiter and Saturn, in their youth, were gravitational bullies, flinging smaller worlds in all directions. Some were ejected entirely, sent spinning off into interstellar space to wander the galaxy forever. Others may have been merely scattered, pushed into distant but still bound orbits where they linger to this day. Planet 9, in this telling, is a survivor, a world that was almost lost but held on, captured in a lonely orbit at the edge of the Sun's influence. But there is another possibility, one that speaks to an even stranger chapter in the solar system's history. What if Planet 9 is not native to our solar system at all? The galaxy is full of wandering planets. Simulations suggest that there may be billions of them in the Milky Way alone. Worlds that formed around other stars, were ejected by gravitational chaos, and now drift through interstellar space with no sun to call home. These rogue planets are, by their nature, almost impossible to detect. They emit no light, reflect nothing, and pass through the darkness between stars like ghosts. But occasionally, very occasionally, one of these wanderers might pass close enough to a star to be captured by its gravity. If it approached at just the right speed, at just the right angle, it could be slowed enough to settle into a distant orbit. Not the tight circular path of a native planet, but a wide, elongated ellipse that keeps it forever at the cold margins of its new home. Could Planet 9 be such a capture? Could the gravitational anomalies in our outer solar system be the signature of an alien world, born around some distant star billions of years ago, drifting through the void for eons before our sun reached out and claimed it? The idea is not new, but it gained traction in the years after Battigan and Brown's announcement. Some researchers noted that a captured rogue planet could explain not just the orbital alignments, but other peculiarities of the outer solar system, the strange tilt of certain trans-Neptunian orbits, the unexplained perturbations in the paths of distant comets. A foreign world arriving from outside might have stirred up the outer solar system in ways that a native planet could not. This hypothesis is beautiful and haunting in equal measure. It would mean that we share our solar system with an immigrant, a world with a history we can never fully know. Where did it come from? What star gave it birth? What catastrophe sent it wandering? These questions would have no answers, only silence stretching back across billions of years and countless light years of empty space. But there is one more possibility, and it is this final hypothesis that makes Planet 9 unlike any astronomical mystery we have ever encountered. In the summer of 2019, two physicists at Harvard University, Amir Siraj and Avi Loeb, published a paper that asked a question so strange it seemed almost like science fiction. What if Planet 9 is not a planet at all? What if it is a black hole? Not a black hole like the ones we usually imagine. The stellar remnants that form when massive stars collapse, or the supermassive giants that lurk at the centres of galaxies. These are objects with origins we understand, forged in the violence of stellar death, or grown over billions of years from the merger of smaller black holes. No, Siraj and Loeb were proposing something different, something older, something that, if it exists, would have formed in the first fraction of a second after the Big Bang itself. They were proposing a primordial black hole. The concept of primordial black holes dates back to the 1970s, when the physicist Stephen Hawking first realised that the extreme conditions of the early universe could have created black holes of almost any size. In the moments after the Big Bang, before atoms existed, before stars existed, before the universe had cooled enough for ordinary matter to form, quantum fluctuations in the fabric of space-time could have been amplified by the rapid expansion of the cosmos. Some of these fluctuations might have been dense enough to collapse directly into black holes, not through stellar processes, but through the sheer intensity of the universe's birth. These primordial black holes, if they formed, could still exist today. Unlike stellar black holes, which require massive stars to create them, primordial black holes could be almost any size, from smaller than an atom to larger than a star. The smallest ones would have evaporated long ago through a process called Hawking radiation, but those above a certain threshold, roughly the mass of an asteroid or larger, could have survived for billions of years, drifting through the universe undetected. And here is where the mathematics becomes unsettling. A primordial black hole with a mass of roughly 5 to 10 Earth masses, the same mass predicted for Planet 9, would have an event horizon about the size of a grapefruit. It would emit no light. It would reflect nothing. It would be, for all practical purposes of visual detection, perfectly invisible. And yet it would exert exactly the same gravitational influence as a planet of the same mass. It would shepherd distant objects into aligned orbits. It would perturb the paths of comets. It would do everything we expect Planet 9 to do, while remaining utterly undetectable by conventional telescopes. This is not science fiction. The mathematics is rigorous. The physics is sound. There is nothing in our current understanding of the universe that says such an object cannot exist, and there is nothing in the observational evidence that can distinguish between a distant planet and a small black hole of the same mass. Both would produce identical gravitational effects. Both would be equally invisible at the distances involved. The difference is what they are. Picture, if you can, the outer reaches of our solar system, that vast, cold, empty region beyond the last familiar world. Now imagine that somewhere in that darkness, not some frozen planet drifting in eternal night, but a hole in space itself. A point where gravity has collapsed matter into infinite density, where time bends and distorts, where anything that crosses the event horizon is lost forever. Not the corpse of a dead star, but something older. Something that has existed since the universe was less than a second old, older than every galaxy, every star, every atom of ordinary matter. And it is here, in our solar system, orbiting our sun. The very idea seems to strain credulity. Black holes are exotic objects, phenomena of the extreme universe, not residents of quiet planetary neighbourhoods. And yet the mathematics does not discriminate. Gravity is gravity. Mass is mass. If something with the mass of 5 Earths orbits the Sun at 600 astronomical units, it will produce certain effects regardless of what that something is. We cannot see Planet 9. We can only see what it does. And what it does is exactly what a primordial black hole would do. Siraj and Loeb proposed a way to test the hypothesis. If Planet 9 is a black hole rather than a planet, it would occasionally interact with material in the outer solar system. Comets, asteroids, the scattered remnants of the Oort cloud. When matter falls toward a black hole, it heats up enormously, emitting radiation that could be detected by sensitive instruments. A black hole at the edge of our solar system might produce brief flares of X-rays or gamma rays as it consumes passing debris, signals that would be invisible to ordinary telescopes but detectable by the right kind of survey. This is the search that is now underway. The Vera C. Rubin Observatory, a new facility in Chile equipped with the most powerful survey camera ever built, is expected to begin operations soon. It will scan the entire southern sky repeatedly, looking for anything that moves, anything that brightens, anything that might betray the presence of an unseen massive object. If Planet 9 is a planet, the Rubin Observatory might finally capture its faint reflected light. If it is a black hole, it might catch the telltale flare of infalling matter. Either way, the mystery may soon be solved. But let us pause here, before the answer comes, and sit with the uncertainty for a moment, because there is something profound in not knowing, in living, as we do now, in a universe where the boundaries of our own solar system contain a genuine enigma. We have mapped the inner planets with exquisite precision. We have sent spacecraft to every major world from Mercury to Neptune, photographed their surfaces, measured their atmospheres, touched their moons with robotic hands. We know our cosmic neighbourhood intimately, and yet beyond the last familiar shore something waits that we cannot identify. It may be a world, it may be a wanderer from the stars, it may be a relic of the universe's first moment of existence, and we do not know which. This is what makes Planet 9 different from other astronomical mysteries. It is not distant, not in the cosmic sense. It is not in another galaxy, not at the edge of the observable universe. It is here, in the same gravitational embrace that holds our own planet in orbit. It is a neighbour, and we have never seen its face. Consider what it would mean if Planet 9 is indeed a planet. A super-Earth, perhaps, with a rocky core wrapped in layers of ice, orbiting in darkness for 4.5 billion years. Such a world would be the largest undiscovered body in our solar system, a new member of our planetary family waiting to be welcomed. Its discovery would rewrite textbooks, inspire missions, give us one more world to explore. It would be strange but wonderful, a gift from the outer darkness. Now consider what it would mean if Planet 9 is a captured rogue, a world born around some other star, ejected into the void, wandering for billions of years before our sun caught it in passing. Such an object would carry a history entirely separate from our own. Its composition might differ from anything else in our solar system. Its isotopic ratios might tell us about the star system where it formed, about processes and environments we have never directly observed. It would be an emissary from the galaxy, a message in a bottle that drifted across light years to reach us. And what would it mean if Planet 9 is a primordial black hole, a piece of the Big Bang itself, a fragment of the universe's first fraction of a second, trapped in orbit around an ordinary yellow star? Such a discovery would transform our understanding of cosmology, of black holes, of the distribution of mass in the universe. It would mean that the early cosmos was stranger and more violent than we imagined, producing black holes in quantities we have yet to fully appreciate. It would mean that our solar system is not merely a collection of planets and moons and asteroids, but a harbour for something far older and far more exotic. Any of these answers would be extraordinary. All of them remain possible. And so we wait, and we search, and we wonder. The mathematics of Planet 9 is solid. The orbital alignments are real. Something is out there, bending the paths of distant objects with its gravity, leaving fingerprints in the dynamics of the outer solar system. But what that something is, what form it takes, what history it carries, what it would mean for our understanding of the universe, remains one of the deepest mysteries in modern astronomy. In the chapters that follow, we will trace the full story of this invisible world. We will follow the astronomers who first noticed the strange orbits, the physicists who proposed the black hole hypothesis, the engineers who are building the instruments that might finally capture an image. We will explore the outer solar system itself, that vast and largely unexplored realm beyond Neptune, where sunlight fades to a memory, and the boundary between our neighbourhood and the interstellar void grows uncertain. And we will ask, again and again, the question that haunts this entire mystery. What does it mean to know something is there when you cannot see it? What does it mean to feel a gravitational pull from the darkness and not know what is pulling? There is one more thing worth understanding before we continue, and it is perhaps the strangest detail of all. The region where Planet 9 is thought to orbit, that distant frozen expanse hundreds of times farther from the Sun than Earth, is not empty. It is populated by a sparse scattering of icy bodies, the outermost remnants of the solar system's formation. And these bodies do not move randomly. They move as if choreographed, their orbits clustered and aligned in ways that should not happen by chance. It is as if they are all responding to the same conductor, all feeling the pull of the same unseen hand. And that hand, whatever it is, has been shaping the outer solar system for longer than life has existed on Earth. Something is out there tonight. It has been out there for billions of years, circling the Sun in an orbit so vast that a single year there would span the entire history of human civilization. It has never been seen, never been photographed, never been visited. It exists only in equations, in orbital mechanics, in the patient accumulation of evidence from 100 different observations. and yet it is as real as the ground beneath your feet, as real as the moon outside your window, as real as anything in the universe can be. It is Planet 9, or it is something else entirely, and the answer, when it finally comes, may change everything we thought we knew about our place in the cosmos. The story of how we came to suspect something lurking in the outer darkness begins, as so many astronomical discoveries do, with a single anomaly. One object behaving strangely, one orbit that refused to make sense. The year was 2003, and a team of astronomers at the Palomar Observatory in California was conducting a systematic survey of the outer solar system, searching for whatever might be hiding in that vast and poorly charted realm beyond Neptune. They were looking for large Kuiper belt objects, the icy remnants of the solar system's formation that drift in slow, cold orbits at the edge of everything. And on a November night, in a series of images captured over several hours, they found something unexpected. It appeared as a faint point of light, moving almost imperceptibly against the fixed background of stars. At first, it seemed like just another distant chunk of ice, another member of the scattered disk population that inhabits the outermost reaches of the solar system. But as the astronomers calculated its orbit, they realized this object was different. It was not simply far away, it was impossibly far away, on an orbit so elongated and so extreme that it would carry the object more than 900 astronomical units from the Sun at its most distant point. 900 times the distance between Earth and the Sun, so far that sunlight reaching it would be dimmer than the glow of a single candle seen from more than a mile away. They named it Sedna, after the Inuit goddess of the sea, a deity who dwells in the coldest depths of the Arctic Ocean. And the name was fitting, because Sedna exists in a realm of cold beyond anything we can truly comprehend. At its closest approach to the Sun, it is still more than 76 astronomical units away, well beyond the orbit of Neptune, well beyond the main Kuiper belt. At its most distant, it would take light more than 5 days to reach it from the Sun. A single orbit takes Sedna more than 11,000 years to complete. The last time Sedna was this close to the Sun, human beings were just beginning to develop agriculture. The pyramids had not yet been built, writing had not yet been invented, and by the time Sedna returns to this point in its orbit, another 11,000 years from now, everything we know of human civilization may have crumbled to dust or transformed into something unrecognizable. But Sedna's extreme distance was not the strangest thing about it. The strangest thing was the shape of its orbit, and more importantly, what that shape implied. Sedna never comes close to Neptune. It never comes close to any of the giant planets. And yet its orbit is highly elliptical, stretched out into a long oval rather than the near circular path you might expect. In orbital mechanics, elliptical orbits are usually the result of gravitational interactions. Something has to pull on an object, perturb its path, stretch its orbit from a circle into an ellipse, but Sedna is too far from the known planets for any of them to have done this. Neptune, the outermost giant, orbits at roughly 30 astronomical units. Sedna's closest approach is more than twice that distance. The known planets simply cannot reach it. So what pulled on Sedna? What shaped its orbit into that long, lonely ellipse? The astronomers who discovered it had no clear answer. They proposed several possibilities. Perhaps a passing star, billions of years ago, had swept through the outer solar system and gravitationally scattered Sedna into its current orbit. Perhaps the Sun was born in a dense stellar cluster, where close encounters with neighbouring stars were common, and Sedna preserves the memory of those ancient perturbations. Perhaps there was something else out there, something massive enough to influence Sedna's orbit, but too distant and too faint to be seen. The question lingered, unanswered and slightly unsettling, for more than a decade, and then more objects began to appear. In 2012, another extreme object was discovered, designated 2012 VP113. Its orbit was similarly stretched, similarly distant, similarly inexplicable. In 2014, another, 2012 GB174, later nicknamed Biden by its discoverers. Each new object had the same peculiar characteristics: orbits that never approach the giant planets, orbits elongated by some unknown force, orbits that seem to cluster together in space, their long axes pointing in roughly the same direction, as if they had all been sculpted by the same invisible hand. By 2016, the sample had grown large enough to see a pattern. 6 of these extreme trans-Neptunian objects shared an uncanny alignment. Their orbits were not randomly distributed around the Sun, as you would expect if each had been shaped by independent processes. Instead, they were clustered, their perihelion points, the places where they pass closest to the Sun, all bunched in the same region of space. The probability of this happening by chance was vanishingly small, less than 1%. Something was causing this alignment. Something was herding these distant objects into formation. And that something, whatever it was, had to be massive. This is where Konstantin Batygin and Michael Brown enter the story. Brown by then was already famous in planetary science circles, though his fame had a bittersweet edge. He was the astronomer most responsible for Pluto's demotion from planetary status, having discovered Eris in 2005, a Kuiper belt object roughly the same size as Pluto. His discovery had forced the International Astronomical Union to reconsider what the word planet meant, leading to Pluto's reclassification as a dwarf planet. Brown wore this legacy with a certain wry humour, titling his memoir How I Killed Pluto and Why It Had It Coming. But beneath the humour was a serious and meticulous scientist, someone deeply familiar with the outer solar system and its populations. Batygin was younger, a theoretical physicist with a gift for celestial mechanics and computer simulations. Together, they made an unlikely but effective team. Brown the observer, intimately acquainted with the data, Batygin the theorist, able to model gravitational dynamics with mathematical precision. And when they looked at the clustering of these extreme objects, they saw something that demanded explanation. Their approach was elegant. Rather than trying to explain each object's orbit individually, they asked a simpler question. What would it take to produce this clustering? What kind of gravitational influence could herd these distant bodies into alignment? They built computer simulations, testing various scenarios. A passing star could not do it. The known planets could not do it. Random chance could not do it. But one scenario worked beautifully. A distant, massive planet on an elongated orbit, positioned in just the right way to shepherd the extreme trans-Neptunian objects into their observed alignment. The planet they proposed was startling in its specifications. It would need to be about 5 to 10 times the mass of Earth, making it a so-called super-Earth, a class of planet that is surprisingly common in other star systems, but entirely absent from our own. It would orbit at an average distance of perhaps 400 to 800 astronomical units, though on an elliptical path that might carry it as close as 200 astronomical units, or as far as 1200. Its orbital period would be measured in tens of thousands of years, perhaps as long as 20,000 years for a single trip around the Sun, and its orbit would be tilted relative to the plane of the solar system, inclined by about 15 to 25 degrees. But here is the crucial detail, the feature that made the hypothesis testable. The proposed planet's orbit would be anti-aligned with the orbits of the clustered objects. Its perihelion, its closest approach to the Sun, would be on the opposite side of the solar system from the perihelia of the objects it was influencing. This anti-alignment is not intuitive, but it emerges naturally from the gravitational dynamics. The distant planet acts as a gravitational shepherd, and the most stable configuration for the smaller objects is to cluster opposite the shepherd, avoiding close encounters while still feeling its long-range influence. Batygin and Brown published their hypothesis in January of 2016 in a paper in the Astronomical Journal that would become one of the most discussed scientific publications of the decade. The title was measured, almost understated, Evidence for a Distant Giant Planet in the Solar System. But the implications were anything but understated. If their analysis was correct, there was a world larger than Earth hiding in the outer solar system, a world that had been shaping the orbits of distant objects for billions of years, a world that no one had ever seen. The response from the astronomical community was intense and immediate. Some researchers were sceptical, arguing that the observed clustering might be an artifact of observational bias. We tend to look at certain parts of the sky more than others, and perhaps the clustering was simply a reflection of where we had pointed our telescopes. Others pointed out that the sample size was small, just 6 objects at the time of the original paper, and that small samples can produce apparent patterns that disappear as more data accumulates. But as more observations accumulated, the evidence strengthened rather than weakened. Additional extreme trans-Neptunian objects were discovered, and most of them fit the predicted pattern. The clustering remained, the alignment persisted, and more remarkably, Batygin and Brown's model made predictions that were subsequently confirmed. They had proposed that Planet 9's gravity would produce objects with orbits perpendicular to the plane of the solar system, objects that would swing far above and below the main disk where most planets orbit. Such objects seemed unlikely, even bizarre, but they exist. They had been discovered even before Batygin and Brown made their prediction, and they fit the model perfectly. This is how science is supposed to work. A hypothesis makes predictions. Observations test those predictions. If the observations match, confidence in the hypothesis grows, and the observations kept matching. By 2019, the evidence for Planet 9 had grown strong enough that Brown and Batygin estimated the probability of its existence at greater than 90%. Not certainty, but close. Something was out there, bending orbits, shaping the outer solar system. The mathematics was clear. The question was only, what form did that something take? And this is where the story takes its strangest turn. For most researchers, the default assumption was straightforward. Planet 9 was a planet. A super-Earth, perhaps, or a mini-Neptune, an ice giant similar to Uranus or Neptune but smaller. Such planets are extraordinarily common in the galaxy. Surveys of other star systems have revealed that super-Earths are among the most abundant types of planets, far more common than gas giants like Jupiter or terrestrial worlds like Earth. Our solar system, conspicuously, lacks one. Perhaps Planet 9 is our missing super-Earth, somehow scattered to the outer solar system during the chaotic early days of planetary formation, or perhaps captured from a passing star system long ago. But there was another possibility, darker and stranger, hiding in the mathematics. In 2019, two physicists at Harvard University, Avi Loeb and Amir Siraj, published a paper that proposed an alternative explanation. What if Planet 9 was not a planet at all? What if it was a primordial black hole? The idea sounds almost absurd at first hearing. A black hole in our solar system. The stuff of science fiction, surely, not serious astrophysics. But primordial black holes are a real theoretical prediction, and Loeb and Siraj's analysis was rigorous. They noted that a primordial black hole with the right mass, about 5 to 15 times the mass of Earth, would produce exactly the same gravitational signature as a planet of equivalent mass. Gravity does not care about the nature of the object producing it, only about the mass. A 5 Earth mass planet and a 5 Earth mass primordial black hole would bend the orbits of distant objects in precisely the same way, and a primordial black hole of this mass would be almost impossibly small. The event horizon of a 5 Earth mass black hole would be roughly the size of a tennis ball. Imagine something heavier than 5 Earths compressed into a sphere you could hold in your hand. It would be utterly dark, utterly invisible, emitting no light of its own. Unlike the supermassive black holes at the centres of galaxies, which betray their presence through the brilliant accretion disks of infalling matter, a primordial black hole in the outer solar system would have almost nothing to consume. It would drift through the emptiness, an invisible singularity, detectable only by its gravitational influence on other objects. It is worth pausing on what a primordial black hole actually is, because the concept is both strange and profound. Ordinary black holes, the ones we detect through gravitational waves and X-ray emissions, form from the collapse of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses inward, and if the star is massive enough, nothing can stop the collapse. The core becomes a black hole, a region of space-time so warped that not even light can escape. But primordial black holes, if they exist, formed through an entirely different mechanism. They are relics of the very early universe, created in the first fraction of a second after the Big Bang. In those earliest moments, the universe was extraordinarily hot and dense, and tiny fluctuations in density were everywhere. Most of these fluctuations were smoothed out as the universe expanded, eventually becoming the seeds of galaxies and galaxy clusters. But some fluctuations may have been so intense, so concentrated, that they collapsed directly into black holes before the universe had even cooled enough to form atoms. These primordial black holes could have formed in a wide range of sizes, from the microscopic to the massive. The smallest would have evaporated long ago through Hawking radiation, the quantum mechanical process by which black holes slowly lose mass and energy. But larger primordial black holes, those with masses comparable to planets, or even greater, would still exist today, drifting through the cosmos as invisible relics of the universe's violent birth. If Planet 9 is a primordial black hole, it would be something almost unprecedented. A piece of the Big Bang itself, captured by our sun's gravity, orbiting at the edge of our solar system for billions of years. It would mean that primordial black holes are not merely a theoretical curiosity, but a real population scattered throughout the galaxy, perhaps even throughout the universe. It would mean that our solar system is far stranger than we ever imagined, harbouring not just planets and moons and asteroids, but a fragment of the first second of cosmic history. But how would we ever know? How could we possibly distinguish between a planet and a primordial black hole, given that both would produce identical gravitational signatures? The answer lies not in gravity, but in light. A planet, no matter how distant, reflects sunlight. A super-Earth at 500 astronomical units would be faint beyond belief, but it would not be completely invisible. The light from the sun, diminished to a whisper by the vast distance, would still illuminate its surface, and a fraction of that light would bounce back toward us. With a sufficiently powerful telescope, with enough exposure time, with the right survey strategy, we might detect that reflected light. The Vera C. Rubin Observatory, currently under construction in Chile, is specifically designed to find faint moving objects in the outer solar system. When it begins operations, it will survey the entire visible sky every few nights, building up a catalogue of everything that moves against the background of stars. If Planet 9 is a planet, the Rubin Observatory has a reasonable chance of finding it within a decade. But a primordial black hole would reflect nothing. It would be absolutely dark, a hole in the fabric of space-time that swallows light rather than reflecting it. Traditional optical surveys would never detect it. They would sweep across its location again and again, registering nothing but empty darkness, while the invisible object continued its eternal orbit, unseen and unseeable. Loeb and Siraj proposed a different approach. A primordial black hole in the outer solar system, they argued, would not be completely isolated. It would occasionally pass through the diffuse cloud of gas, dust and small particles that pervades the outer solar system. As matter fell toward the black hole's event horizon, it would be accelerated to tremendous speeds, and some of this matter would emit radiation before crossing the point of no return. The black hole might produce brief flares of light or radio waves, transient signals that would flicker against the darkness. More speculatively, the black hole might occasionally consume a comet or asteroid, producing a more dramatic burst of radiation. These events would be rare, perhaps exceedingly rare, but they would be distinctive. A search for such transient signals, combined with careful monitoring of the predicted orbital path, might eventually reveal the presence of a primordial black hole. Another possibility involves gravitational microlensing. When a massive object passes between us and a distant background star, its gravity bends the light from that star, causing the star to appear temporarily brighter. This effect is routinely used to detect exoplanets and to search for dark objects in the galaxy. If Planet 9 is a primordial black hole, and if it happens to pass in front of a background star, that star would briefly brighten in a characteristic way. The probability of such an alignment is small, given the vastness of space, but it is not zero. Dedicated microlensing surveys, watching millions of stars night after night, might eventually catch the black hole in the act of bending starlight. For now, though, we are left with a profound uncertainty. The gravitational evidence for something massive in the outer solar system continues to accumulate. The clustering of extreme trans-Neptunian objects remains real and unexplained by any known phenomenon. The models of Batygin and Brown continue to make successful predictions. Something is out there. Something with the mass of several Earths. Something that has been shaping the outer solar system for longer than life has existed on Earth. But whether that something is a captured rogue planet, wandering into our solar system from interstellar space, or a super-Earth formed in the primordial disk of gas and dust that surrounded the young sun and scattered outward through gravitational interactions, or a primordial black hole, a piece of the universe's first moment, trapped in orbit around an ordinary star, this remains unknown. Each possibility carries its own staggering implications. Each would force us to revise our understanding of the cosmos in profound ways. And so, the search continues. Astronomers point their telescopes at the regions of sky where Planet 9 is most likely to be found, slowly scanning the darkness for a faint point of light or an unexpected flicker of radiation. The Vera Rubin Observatory prepares to begin its decade-long survey, armed with the largest camera ever built for astronomy, capable of imaging immense swaths of sky in a single exposure. Theorists refine their models, narrowing the predicted orbit, calculating the most probable locations, preparing for the moment when observation finally catches up with mathematics. It is a strange feeling, knowing that something is out there and being unable to see it. We have grown accustomed to the idea that the universe reveals itself to those who look carefully enough, that every mystery eventually yields to persistent observation. But Planet 9 has resisted our gaze for nearly a decade now. It remains hidden, not because our instruments are primitive, but because the outer solar system is so vast, so dark, so cold that even a world larger than Earth can vanish into the shadows. Consider the scale of the search. The region where Planet 9 is thought to orbit spans thousands of square degrees of sky. The object itself, if it is a planet, would be fainter than magnitude 25, dimmer than a candle seen from the other side of the planet. Distinguishing it from the countless fixed stars in the background requires patience, precision, and time. You must image the same patch of sky repeatedly, looking for anything that moves. You must rule out asteroids, comets, satellites, glitches in the detector. And even when you have done all of this, you may simply be looking in the wrong direction, searching a region of sky where Planet 9 is not. There is something almost meditative about this kind of search. Night after night, month after month, year after year, astronomers accumulate images, build databases, write algorithms to sift through the data. They are not looking for the spectacular or the obvious. They are looking for the faintest whisper of light, the slightest deviation from randomness, the barest hint that something is there. It is a practice of patience, a discipline of attention, a willingness to stare into the darkness and wait for the darkness to reveal its secrets, and in the meantime, the theoretical possibilities multiply. Perhaps Planet 9 is not a single object, but a swarm of smaller bodies, their combined gravity mimicking the effect of a single, large planet. Perhaps the clustering of trans-Neptunian objects is indeed observational bias, a trick of incomplete data that will disappear as more objects are discovered. Perhaps there is something even stranger going on, some modification of gravity or some exotic population of objects that we have not yet imagined. Each of these possibilities has been explored, each has been found wanting, at least partially. The swarm hypothesis struggles to explain the precise alignment of orbits. The bias hypothesis has been tested and found insufficient to account for the observed clustering, and modifications of gravity, while always worth considering, face the steep challenge of explaining why standard Newtonian mechanics works so well everywhere else in the solar system, while failing specifically in the outer reaches. The simplest explanation remains the original one, a massive body, orbiting far beyond Neptune, shaping the dynamics of the outer solar system through its gravity. The simplest explanation is not always correct, but it is often a good place to start. What would it feel like, one wonders, to be the astronomer who finally finds it? To sit at a computer terminal reviewing the night's observations and notice something moving against the stars? To realise with growing certainty that you're looking at a world no human eye has ever seen, a world that has been hiding in the darkness since before our species existed? There is a moment in every great discovery when the universe opens a door and invites you through. The astronomers searching for Planet 9 are waiting for that door to open. They know it exists. They can feel the gravitational pull of what lies beyond. But the door remains closed, for now, and all they can do is keep searching. And while they search, while the telescopes sweep their patient arcs across the frozen darkness, there is another question that waits beside them. It is a question that most discussions of Planet 9 mention only briefly, then set aside. It is a question that seems, at first, almost impolite to ask. We have assumed, throughout all of this, that we know what we are looking for. We have assumed that Planet 9, if it exists, is a planet, a world of rock and ice and perhaps a thick atmosphere, a sibling to the planets we already know, just colder and more distant and impossibly far from the light. But the mathematics that reveal Planet 9's presence tell us only about its gravity. They tell us that something massive is out there, something with roughly 5 to 10 times the mass of Earth, something orbiting at a distance of 400 to 800 astronomical units. The mathematics do not tell us what that something is made of. The mathematics do not tell us where it came from. The mathematics tell us only that gravity is being exerted, that orbits are being bent, that something is pulling on the outer solar system with a steady, patient hand. And this opens a door to possibilities that are stranger than any we have considered so far. Let us begin with the gentlest of these possibilities, the one that astronomers consider most likely, the one that feels like the natural extension of everything we know about planetary formation. Perhaps Planet 9 is a super-Earth. Perhaps it formed in the inner solar system, in the crowded disk of gas and dust that surrounded the young sun 4.5 billion years ago. In that chaotic nursery, where worlds were constantly jostling for position, where gravitational encounters sent planets careening toward the sun or outward into the void, perhaps one ice giant was unlucky enough to stray too close to Jupiter or Saturn. Perhaps it was flung outward on a long looping orbit, climbing away from the sun with tremendous speed, yet not quite fast enough to escape entirely. It would have settled into a distant orbit, cooling in the darkness, its atmosphere freezing into frost, its internal heat slowly radiating away into the void. Over billions of years, it would have become what it is now, a cold, dark world, invisible against the black, carrying within its frozen layers the chemistry of the inner solar system, a record of conditions that existed before the Earth was fully formed. This is the standard story, the one that appears in most scientific papers about Planet 9. It is elegant in its simplicity. It requires no new physics, no exotic objects, no visitors from interstellar space. It requires only the ordinary chaos of planetary formation, the gravitational pinball that we know shaped the solar system in its youth. And if this is what Planet 9 turns out to be, it will still be extraordinary. It will be a window into the earliest epochs of our solar system, a fossil from an era we can barely imagine. To study its atmosphere, its composition, its internal structure, would be to learn something profound about the conditions that gave rise to all the worlds we know, including our own. But there is another possibility, one that is slightly stranger, one that asks us to expand our understanding of where planets can come from. Consider that our sun did not form alone. Stars almost never do. They are born in clusters, in vast nurseries of gas and dust where hundreds or thousands of stellar siblings emerge from the same collapsing cloud. The sun's birth cluster has long since dispersed, its members scattered across the galaxy, their shared origin written only in the chemical fingerprints they carry. But in those early days, when the sun was still young and its cluster was still intact, the gravitational environment was far more complex than it is today. Stars passed close to one another, planetary systems interacted, and in those close encounters, planets could be torn from their parent stars, sent drifting into the interstellar medium, becoming what astronomers call rogue planets. Rogue planets wander the galaxy in staggering numbers. We are only beginning to appreciate how common they are. Some estimates suggest there may be billions of them in the Milky Way alone, perhaps more rogue planets than there are planets bound to stars. They drift through the darkness between stellar systems, carrying no sun, receiving no warmth, their surfaces locked in eternal night. Most of them will wander forever, never encountering another star, never being captured into another orbit. But a very few, may pass close enough to a star to be caught. And this raises a possibility that is both thrilling and humbling. What if Planet 9 is not a native of our solar system at all? What if it is a wanderer, a refugee from another star, a world that was born in orbit around a different sun and was torn away by gravitational violence billions of years ago? What if it drifted through interstellar space for unimaginable spans of time, and then, by the rarest of chances, passed close enough to our sun to be captured? The mathematics would be the same. The gravitational influence on the outer solar system would be indistinguishable. We could not tell, from the orbital dynamics of trans-Neptunian objects alone, whether Planet 9 was born here or arrived from beyond. Only by studying its composition, its isotopic ratios, its atmospheric chemistry, could we hope to determine its origin. And even then we might not be certain. The universe, after all, is remarkably uniform in its building blocks. The elements that make up distant worlds are the same elements that make up our own. The differences lie in the proportions, in the ratios of isotopes, in the subtle chemical signatures that record the conditions under which a world was formed. Imagine, for a moment, what it would mean to discover that Planet 9 is an alien. Not alien in the sense of harbouring life, though that possibility opens its own doors. Alien in the sense of belonging to another stellar family, of carrying the chemistry of a different cosmic nursery. It would mean that our solar system has adopted a child from across the galaxy. It would mean that the boundary between our planetary family and the wider universe is more porous than we ever imagined. It would mean that worlds can travel between stars, that the distances that seem so vast to us are, over geological timescales, not barriers at all, but highways. And yet, as strange as this possibility seems, there is one that is stranger still. There is one possibility that has been raised, tentatively, speculatively, by serious astronomers and physicists, and it asks us to reconsider not just what Planet 9 is, but what we mean by an object at all. In 2019, two researchers at Harvard University published a paper that asked a simple question. What if Planet 9 is not a planet? What if the gravity that shapes the outer solar system, the invisible hand that bends the orbits of distant objects, belongs to something far more exotic? What if Planet 9 is a primordial black hole? The idea sounds almost absurd at first. Black holes, we think, are the corpses of massive stars collapsed under their own gravity into singularities of infinite density. They are phenomena of unimaginable violence, forged in supernova explosions, surrounded by disks of superheated matter, announcing their presence with bursts of radiation that can be detected across the universe. What would a black hole be doing in the quiet darkness of the outer solar system, gently nudging icy bodies into aligned orbits? But primordial black holes are different. They would not have formed from stellar collapse. They would have formed in the earliest moments of the universe, in the first fraction of a second after the Big Bang, when the cosmos was so dense and so hot that tiny fluctuations in density could collapse directly into black holes without needing a star to die first. These black holes could be small, much smaller than any black hole formed from a star. A primordial black hole with the mass of 5 Earths would be roughly the size of a small orange. It would be invisible in visible light, emitting only the faintest trickle of Hawking radiation, far too dim to detect from Earth. It would exert exactly the same gravitational influence as a planet of the same mass, and it would be effectively impossible to distinguish from a planet using gravitational observations alone. This is the hypothesis that Avi Loeb and his colleague Amir Siraj proposed. They did not claim that Planet 9 is a black hole. They simply pointed out that a primordial black hole would be consistent with the data, that it would explain the orbital clustering just as well as a super-Earth, and that distinguishing between these possibilities would require new observational strategies. They suggested searching for gamma rays or other radiation that might be produced if the black hole were accreting matter from the interstellar medium, the thin soup of gas and dust that permeates even the emptiest regions of space. They acknowledged that the probability was low, but they argued that the stakes were high enough to make the search worthwhile. Consider what it would mean to discover a primordial black hole in our own solar system. It would be the first direct evidence that such objects exist at all. It would confirm a prediction that has lingered at the edge of theoretical physics for decades. It would open a window into the earliest moments of the universe, into conditions that existed before atoms formed, before light could travel freely, before anything resembling the cosmos we know today had come into being. A primordial black hole is a fossil from the Big Bang itself, a relic of an epoch so violent and so brief that it has left almost no other traces. To find one, to study one, to understand its properties, would be to touch the very origin of everything. And there is something else, something that the more cautious discussions of this hypothesis often leave unspoken. A primordial black hole in the outer solar system would be profoundly strange in a way that even the discovery of an alien planet would not be. A planet, however exotic, is still matter. It is still atoms and molecules, pressure and temperature, a thing that exists in space and time in a way we can intuitively grasp. A black hole is something else entirely. It is a rupture in the fabric of space-time, a region where the rules we have learned about physics break down, where gravity becomes so strong that nothing, not even light, can escape. To discover that such an object has been orbiting our sun all along, invisible and patient, shaping the outer solar system with its gravity while hiding behind the darkness, would force us to reconsider everything we think we know about our cosmic neighbourhood. The researchers who proposed this hypothesis were careful to emphasize its speculative nature. The probability that Planet 9 is a black hole is almost certainly lower than the probability that it is a planet. But almost certainly is not certainly, and in science, even a small probability is worth investigating when the potential discovery would be transformative. And so the search continues, but with a new dimension added to it. Astronomers looking for Planet 9 are now also keeping their eyes open for the signatures that might distinguish a black hole from a planet. They are watching for gamma-ray flares, for the faint glow of accreting matter, for any signal that might suggest something more exotic than rock and ice. They are not expecting to find these signals, but they are prepared for the possibility. It is worth pausing on the emotional landscape of this search. The astronomers who have dedicated their careers to finding Planet 9 are not, for the most part, hoping to discover a black hole. They are hoping to discover a planet, a new world, a companion to the worlds we already know. There is something deeply satisfying about the idea of completing our map of the solar system, of finding that last hidden sibling and welcoming it into the family. A planet can be studied, photographed, perhaps one day even visited by robotic spacecraft. A planet has weather and geology and chemistry. A planet is a place. A black hole is not a place in the same way. A black hole is an absence, a hole in the universe, a phenomenon rather than a thing. To discover that Planet 9 is a black hole would be scientifically extraordinary, but it would carry with it a certain loss. We would not be able to photograph its surface, study its atmosphere, imagine what it might look like from orbit. We would only be able to observe its effects on the space around it, infer its properties from the ways it bends light and captures matter. It would be present only through its absences, and yet, there is a strange beauty in this possibility too. If the outer solar system harbours a primordial black hole, then we have been living beside a piece of the universe's birth for all of human history without knowing it. Every night, while we have gazed at the stars and wondered about our place in the cosmos, this tiny fragment of the Big Bang has been out there, silent and dark, carrying within its infinitesimal volume the memory of everything that came before time began. It would be the oldest thing in the solar system by an unimaginable margin. The Sun is 4.5 billion years old. A primordial black hole would be as old as the universe itself, nearly 14 billion years, a witness to everything that has ever happened, even if it has witnessed nothing because no light has ever escaped its grasp. There is one more possibility we should consider, one that sits at the boundary between astronomy and philosophy. What if Planet 9 does not exist at all? What if the orbital clustering that Batyjin and Brown discovered is explained by something else entirely? Something we have not yet imagined. Something that will reveal itself only when we have gathered more data, discovered more trans-Neptunian objects, refined our understanding of the outer solar system's dynamics. This is not the most popular hypothesis among the researchers who study this question, but it is one that honest scientists must hold in reserve. The history of astronomy is filled with objects that seem to exist. Objects that explained anomalies in the data, objects that were given names and searched for with great determination, only to vanish when better observations revealed that the anomaly had a different explanation. The planet Vulcan was postulated in the 19th century to explain a slight irregularity in Mercury's orbit. Astronomers searched for it for decades, convinced that it must exist. But Vulcan did not exist. The irregularity was explained eventually by Einstein's general theory of relativity, which showed that Mercury's orbit was being affected by the curvature of spacetime near the Sun, not by the gravity of an unseen planet. The mathematics that seemed to require Vulcan were correct, but the interpretation was wrong. Could the same be true of Planet 9? Could the orbital clustering that seems to require a massive perturber turn out to be explained by something else, something we have not yet discovered? Perhaps there is a subtle effect in the dynamics of the outer solar system that we have not accounted for. Perhaps the clustering is the result of gravitational interactions among the trans-Neptunian objects themselves, a self-organizing phenomenon that emerges from the collective behavior of thousands of small bodies. Perhaps there is something about the way we have collected our data that has introduced a bias we have not recognized. These possibilities cannot be ruled out. They are part of the landscape of scientific uncertainty that surrounds Planet 9. But they are not the leading hypotheses, and for good reason. The clustering is too pronounced, too statistically significant to be easily explained away. The objects whose orbits are aligned are separated by such vast distances that they cannot plausibly interact with one another through any known mechanism. The alternative explanations that have been proposed have been tested and found insufficient. The gravitational influence of a distant massive body remains the simplest, most elegant explanation for what we observe. And so we return to the darkness, to the patient search, to the question that has no answer yet. Planet 9 waits for us in the outer reaches, silent and cold and far from the light. It may be a super-Earth, born in our solar system and flung outward by the chaos of youth. It may be a rogue planet, captured from interstellar space, an immigrant from another star. It may be something stranger still, a primordial black hole, a fragment of the Big Bang, a hole in the fabric of reality that has been hiding among us since before the sun was born. Or it may not exist at all, a mathematical phantom that will dissolve when we finally understand what is really happening in the darkness beyond Neptune. The uncertainty is not a failure. It is the shape of the question itself. We are standing at the edge of knowledge, looking outward into a region of space so vast and so dark that even our most powerful telescopes struggle to illuminate it. We know that something is out there. We can feel its presence in the mathematics, in the bent orbits, in the aligned arguments of perihelion. But we cannot see it. We cannot photograph it. We cannot confirm its existence with the simple, direct observation that would settle the matter once and for all. And perhaps that is exactly as it should be. There is something fitting, even beautiful, about the way Planet 9 has revealed itself to us. Not through light, but through influence. Not through seeing, but through inferring. Not through the crisp clarity of a photograph, but through the patient accumulation of evidence gathered one distant object at a time. This is how science often works at its edges, in the places where knowledge thins and uncertainty blooms. We do not always get to see what we are looking for. Sometimes we must learn to know things differently, to trust the mathematics even when the light fails us. Consider, for a moment, how many things in the universe we know only through their effects. We cannot see the wind, but we can feel it against our skin, watch it bend the trees, hear it whisper through the leaves. We cannot see gravity, but we can feel its pull, observe its shaping of orbits and tides and the very structure of the cosmos. We cannot see dark matter, that mysterious substance that makes up most of the matter in the universe, but we can see its gravitational influence on galaxies, the way it bends light and holds clusters together that would otherwise fly apart. In a sense, Planet 9 belongs to this tradition of invisible presences, forces and objects that reveal themselves not through direct observation, but through the traces they leave behind, the fingerprints impressed upon the motions of other things. And perhaps there is something poetic in this, something that speaks to the nature of our quest to understand the universe. We are small creatures on a small planet, looking outward into vastness that exceeds our ability to comprehend. We cannot travel to the outer solar system, cannot send our spacecraft to photograph Planet 9 in any reasonable time frame. Even if we launched a mission today, it would take decades to reach the region where Planet 9 might be hiding, and by then, the question might already be answered by telescopes on Earth or in orbit. We are limited by distance, by time, by the finite speed of light and the constraints of our technology. And yet we persist. We gather data. We build models. We refine our understanding. We inch closer to the truth, even when that truth remains frustratingly out of reach. The search for Planet 9 has become in many ways a meditation on the limits of knowledge itself. It forces us to confront what we can know and how we can know it. It reminds us that the universe does not always cooperate with our desire for clear answers. Sometimes the cosmos keeps its secrets, at least for a while. And in that keeping, there is a kind of invitation, a challenge to look harder, to think deeper, to remain humble in the face of all that we do not yet understand. Let us sit for a moment with the possibility that Planet 9, whatever it is, represents something about the nature of discovery that we have perhaps forgotten in this age of instant information. We live in a time when so much seems knowable, when the answer to almost any question is just a few keystrokes away. We have grown accustomed to certainty, to the comforting illusion that everything worth knowing has already been discovered, catalogued, and made accessible. But Planet 9 reminds us that there are still mysteries in our own cosmic backyard, questions that cannot be answered by searching a database, secrets that will yield only to years of patient observation and careful thought. The astronomers who search for Planet 9 understand this. They wake each morning knowing that the object they seek may not exist, that their careers might be spent chasing a mathematical ghost, and yet they continue. They apply for telescope time, they analyse data, they refine their predictions, they publish papers that will be scrutinised and tested and perhaps ultimately proven wrong. This is what it means to do science at the frontier. It is not triumphant, it is not glamorous, it is patient and uncertain and humble. It is the slow accumulation of knowledge in the face of vast ignorance, the gradual expansion of the circle of light into the surrounding darkness. Return with me one more time to the mathematics that started this journey. The equations that describe planetary motion were worked out centuries ago, refined and perfected until they became tools of extraordinary precision. We can calculate the position of Neptune to within a few kilometres, even though it orbits more than 4 billion kilometres from the Sun. We can predict eclipses centuries in advance, chart the paths of comets, track the wanderings of asteroids. The mathematics of gravity is one of the great triumphs of human intelligence, a system of thought so powerful that it allows us to reach across unimaginable distances and understand the motions of objects we will never touch. And it is this same mathematics that now points towards something unknown. The equations work. The predictions are testable. The clustering of the trans-Neptunian objects is a phenomenon that demands explanation. Konstantin Batygin and Mike Brown did not invent this evidence. They discovered it in the data, saw a pattern that others had overlooked, and proposed a hypothesis that could account for what they observed. Their work has been tested and retested, challenged and defended, refined and extended, and still the evidence holds. Still the mathematics points toward the darkness and says, something is there. There is one more thing worth understanding about the search for Planet 9, something that connects it to the deepest questions we can ask about our place in the cosmos. If Planet 9 exists, if it is a captured rogue planet, then it represents a kind of cosmic visitor, a messenger from another stellar system that has taken up residence in our own. And if this is true, it raises a haunting question. How many other visitors might there be? How many other objects from distant stars might be drifting through our solar system, too faint and too far to be detected, passing through on journeys that began billions of years ago around suns we will never see? The universe, it turns out, is not as empty as it appears. The spaces between stars, which seem so vast and so barren, are in fact filled with wandering objects, worlds without suns, fragments of distant planetary systems that were expelled during the chaos of their formation. Some of these objects are small, mere rocks and ice, but others are massive true planets that carry with them the gravitational heft of worlds. And these rogue planets drift through the galaxy in numbers beyond counting, outnumbering perhaps the stars themselves. Picture, if you can, the Milky Way not as a collection of bright points, but as a sea of darkness filled with hidden travellers. Between every pair of stars there may be dozens, hundreds, perhaps thousands of free-floating worlds. Some of them burn hot with residual heat from their formation, their interior still glowing with the warmth of ancient gravitational compression. Others have cooled to temperatures barely distinguishable from the cosmic background, balls of ice and rock and gas drifting silently through the void. Most of them will never encounter another object, will never be captured by another star, will simply drift on through eternity, alone and unobserved. But occasionally, rarely, one of these wanderers passes close enough to a star to be caught. The mathematics of gravitational capture is complex and improbable, requiring just the right combination of approach angle and velocity, just the right conditions to transform a passing encounter into a permanent relationship. Most rogue planets that approach our solar system would simply swing past, their trajectories bent by the sun's gravity but not captured by it, continuing on their journey through the galaxy, perhaps slightly changed but ultimately free. But now and then the circumstances align, and a wanderer finds a home. If Planet 9 is such a visitor, then it carries with it a history that predates our entire solar system. Its atoms were forged in a different stellar furnace, its ice crystallized from gases that never felt our sun's warmth, its rocky core condensed from the dust of an alien stellar nursery. It would be, in a very real sense, a piece of another world, a physical connection to a stellar system that may no longer exist, a star that may have burned out billions of years ago, planets that may have been consumed or scattered or frozen in the darkness. Consider for a moment what it would mean to touch such an object, to send a spacecraft to orbit it, to study its composition and structure. We would be studying not just another planet, but another history, another pathway through the grand experiment of planetary formation. We would learn how similar or different worlds can be when they form around different stars, under different conditions, with different abundances of elements. It would be like finding a fossil from another timeline, a branch of cosmic evolution that diverged from our own before the sun was born. Spare a thought too for the improbability of such a capture. The galaxy is vast beyond description, and the spaces between stars are so empty that light itself takes years to cross them. For a rogue planet to be captured by our sun, it would have had to approach at just the right angle, with just the right velocity, encountering perhaps one of the outer planets in a way that shed enough energy to trap it in orbit. The probability of any single encounter resulting in capture is vanishingly small. But the universe is old, and the galaxy is filled with wanderers. Over 4.5 billion years, our solar system has had countless opportunities to interact with passing objects. Most of those encounters resulted in nothing, brief gravitational handshakes between strangers who continued on their separate ways. But if even one encounter in a billion resulted in capture, there might be visitors among us, objects that call our solar system home but were born under different suns. It is worth pausing on the way this possibility reshapes our understanding of what a planetary system is. We have grown accustomed to thinking of our solar system as a coherent family, a group of objects that form together from the same primordial cloud of gas and dust, siblings in the cosmic sense, sharing a common origin and a common chemistry. The sun is the parent, the planets are the children, and the minor bodies are the extended family, all tracing their ancestry back to the same gravitational collapse 4.5 billion years ago. But if Planet 9 is a captured object, then our family has adopted a member. There is a foster child among the siblings, an immigrant who has become naturalized, an outsider who has been welcomed into the fold. This does not diminish the object's place in our solar system. It does not make it less worthy of study or less interesting as a scientific target. If anything, it makes it more fascinating, a window into a history we could not otherwise access, a bridge between our solar system and the wider galaxy. And then there is the other possibility, the one that unsettles in a different way. The possibility that Planet 9 is not a planet at all, but something far stranger. A primordial black hole. Let us sit for a long moment with what this would mean. A black hole is a region of space-time where gravity has become so intense that nothing, not even light, can escape. We usually think of black holes as the corpses of massive stars, objects that form when a star many times more massive than our Sun exhausts its nuclear fuel and collapses under its own weight. These stellar black holes are violent and dramatic, born in the catastrophic explosions we call supernovae, marked by the brilliant deaths of giant stars. But there is another kind of black hole, one that was not born from a dying star at all. In the first fraction of a second after the Big Bang, the universe was a cauldron of unimaginable density and temperature. Space itself was compressed. Matter and energy packed so tightly that conditions may have allowed for the direct collapse of regions of space-time into black holes without any stellar intermediary. These primordial black holes, if they exist, would be relics of the universe's first moments, survivors from an epoch before the first stars were born, before the first galaxies formed, before any of the structures we recognize today existed. The mass of a primordial black hole could vary enormously, depending on the size of the region that collapsed. Some might be tiny, microscopic, with masses smaller than a mountain. These would have already evaporated through a process called Hawking radiation, the quantum mechanical effect by which black holes slowly emit particles and shrink over time. But others might be much larger, massive enough to survive for billions of years, massive enough to still be drifting through the universe today, invisible and nearly undetectable. In 2019, a team of physicists at Harvard proposed a startling hypothesis. They suggested that the gravitational evidence pointing toward Planet 9 might not indicate a planet at all. Instead, it might indicate a primordial black hole with a mass of perhaps 5 to 10 times that of Earth, orbiting in the outer solar system, so far from the Sun that it is effectively invisible despite its extreme gravitational influence. The idea seems wild, almost fantastical. But it is not impossible. A primordial black hole of the right mass would exert exactly the same gravitational influence as a planet of the same mass. From the perspective of the trans-Neptunian objects whose orbits are aligned, it would make no difference whether they were being shepherded by a super-Earth or by a black hole. Gravity does not care about the nature of the object doing the pulling. Mass is mass, regardless of its form, and here is the unsettling thought. We might never be able to tell the difference by gravitational observations alone. If the clustering of the trans-Neptunian objects is caused by a massive body in the outer solar system, the mathematics will be the same whether that body is made of rock and ice or whether it is a hole in space-time. To distinguish between these possibilities, we would need to observe the object directly to see whether it reflects light or emits heat or interacts with its environment in ways that only a physical body could. A primordial black hole would do none of these things. It would simply sit there in the darkness, pulling on the objects around it, warping space-time according to the same equations Einstein wrote a century ago, utterly invisible to any telescope that relies on light. We could search forever with our most powerful instruments and never see it, because there would be nothing to see. It would be a perfect absence, a hole in the fabric of reality that reveals itself only through its gravitational grip on the things around it. There is something profoundly strange about this possibility, something that brushes against the limits of what we think we know about the universe. We are accustomed to thinking of objects as things that can be seen, touched, photographed. We are used to the idea that if something exists, there should be a way to observe it directly, to capture an image of it, to confirm its presence with our own senses or with instruments that extend those senses. But a primordial black hole defies this intuition. It exists, in the fullest physical sense. It has mass, it has location, it influences the things around it. But it has no surface, no boundary we could touch, no light we could photograph. It is real in every measurable way, and yet it is utterly invisible. If such an object exists in our solar system, it would represent a fragment of the Big Bang itself, a piece of the first moment of creation that has survived for nearly 14 billion years, drifting through the cosmos, eventually captured by our sun, or perhaps formed in our vicinity when the universe was still young. It would be one of the oldest objects we could ever hope to study, a relic from an epoch so remote that the universe was still a soup of quarks and gluons before atoms existed, before any of the matter that now makes up stars and planets and people had assembled into familiar forms. And here we are, perhaps just a few hundred astronomical units away from it, unable to see it, unable to reach it, knowing it only through the ghostly traces it leaves on the orbits of distant ice worlds. It is enough to make one feel very small and very humble, standing at the edge of knowledge and looking into a darkness that may contain something more ancient than the stars. There is one more thing worth understanding about primordial black holes, something that connects this possibility to the deepest mysteries of modern physics. We do not know whether primordial black holes actually formed in the early universe. The conditions that would have been necessary for their formation are extreme and uncertain. The physics of the first fraction of a second after the Big Bang is among the most speculative in all of science, touching on questions about the nature of gravity, the behaviour of space-time at extreme densities, the transition from the quantum to the classical. We have theories, we have models, we have educated guesses, but we do not have direct evidence. No primordial black hole has ever been observed. But if one were found in our solar system, it would change everything. It would confirm that primordial black holes exist, that the early universe was capable of creating them, that the conditions we have theorized were real. It would open a window onto physics we cannot probe any other way, a laboratory for studying extreme gravity that we carry with us in our own cosmic backyard. It would be, without exaggeration, one of the most important discoveries in the history of science. And this is the paradox of Planet 9. The object that may or may not exist in our outer solar system is important regardless of what it turns out to be. If it is a super-Earth, it tells us something profound about planetary formation. If it is a captured rogue planet, it connects us to the wider galaxy in ways we never imagined. If it is a primordial black hole, it rewrites our understanding of the early universe. And even if it turns out not to exist at all, the search for it has taught us extraordinary things about the outer solar system, about the population of trans-Neptunian objects, about the limits of our observational capabilities. The search itself has value, regardless of the outcome. This is one of the great lessons of scientific inquiry, one that is easy to forget in a culture that prizes only results. The journey matters, the questions matter, the patient accumulation of evidence, the careful testing of hypotheses, the willingness to be wrong and to revise and to continue. These are the practices that have built our understanding of the cosmos. Planet 9, whether it exists or not, has already contributed to this enterprise, has already expanded our knowledge, has already pushed us to look harder and think more carefully about the universe we inhabit. And so we find ourselves in a curious position, suspended between knowing and not knowing, between the mathematics that insists something is out there and the darkness that refuses to reveal itself. This is where science often lives, in the spaces between certainty and doubt, and there is something strangely beautiful about dwelling here for a while, about letting the uncertainty wash over us without demanding immediate resolution. Consider what it means to search for something you cannot see. The astronomers who spend their nights scanning the outer solar system are not simply pointing telescopes at empty space and hoping for luck. They are engaged in a kind of conversation with the cosmos, asking questions through their instruments, listening for answers in the faintest possible signals. Each observation is a sentence in this dialogue, each negative result a response that says, "Not here, not yet, keep looking." And they do keep looking, night after night, year after year, with a patience that borders on the devotional. There is something almost sacred about this kind of persistence, this willingness to search for what may never be found, to continue asking even when the universe seems determined not to answer. The tools of this search are themselves remarkable, each one a testament to human ingenuity and the desire to see what lies beyond the reach of unaided eyes. The telescopes that scan the outer solar system are not the gleaming domes of popular imagination, though some of them are housed in such structures. They are complex instruments, sensitive to wavelengths of light that human eyes cannot perceive, capable of detecting objects so faint that their light has been travelling toward us for hours before it reaches the detector. The images they produce do not look like photographs in any conventional sense. They are data, really, streams of numbers that must be processed and analysed before they reveal anything that looks like an object in space. And even then, the objects they might reveal would appear as nothing more than tiny points, barely distinguishable from the background noise of cosmic rays and distant stars and the electronic hum of the instruments themselves. The search for Planet 9 relies on a technique that astronomers have refined over centuries, the patient comparison of images taken at different times. An object in our solar system will move against the background of fixed stars, tracing a slow arc across the sky as it pursues its orbit around the Sun. But an object as distant as Planet 9 would move almost imperceptibly, shifting by perhaps only a few arc-seconds over the course of a year, a distance so small that it requires the most careful measurements to detect. And the farther away the object, the fainter it would be, the slower it would move, the harder it would be to distinguish from the countless background sources that litter any deep image of the sky. Imagine, if you can, the dedication this requires. An astronomer sits before a screen comparing images taken months or years apart, looking for a single point of light that has shifted position while everything around it has remained fixed. The images are crowded with stars, with galaxies, with artifacts and noise, and somewhere among all of this may be the faint signature of a world that has never been seen before. It is like searching for a particular grain of sand on a beach at night, with only a small flashlight and the knowledge that the grain you seek is moving, almost too slowly to perceive, among billions of others that look almost exactly the same. And yet astronomers persist because the prize is worth the effort, because the question is too important to leave unanswered, because the human spirit cannot resist a mystery. There is something in us that needs to know, that cannot rest while there are shadows at the edge of our maps, that feels compelled to shine light into every dark corner of existence. This is the drive that sent explorers across unmapped oceans, that pushed climbers toward the summits of unclimbed peaks, that carried spacecraft to the outer reaches of the solar system. It is the same drive that keeps astronomers searching for Planet 9, decade after decade, even as the object refuses to reveal itself. The technology of this search has advanced remarkably in recent years. New surveys are coming online that will scan vast swaths of the sky with unprecedented sensitivity and speed. The Vera C. Rubin Observatory, under construction in Chile, will conduct a survey of the entire visible sky every few nights, building up a moving picture of the cosmos that will reveal any object that changes position or brightness over time. If Planet 9 exists and is bright enough to be detected, this survey should find it within a few years of beginning operations. The anticipation in the astronomical community is palpable, a sense that after years of searching with inadequate tools, we may finally have the instruments capable of answering the question one way or another. But we must be prepared for the possibility that even these powerful new tools will come up empty. Planet 9, if it exists, may be fainter than predicted, may be located in a part of the sky that is particularly difficult to search, may for reasons we do not yet understand remain beyond our reach for years or decades to come. The universe is under no obligation to make its secrets easy to uncover, and some mysteries may outlast the patience of any individual searcher. This is why the search is conducted by a community, rather than by isolated individuals, why each generation of astronomers passes the question to the next, why the pursuit of knowledge is a relay race rather than a sprint. It is worth pausing on what happens if the search continues to come up empty, if years pass and no Planet 9 is found. This would not mean that the search was a failure, not in any meaningful sense. It would mean that we have learned something important about the outer solar system, that we have constrained the possibilities, that we have ruled out certain regions of space and certain types of objects. In science, a negative result is still a result, a piece of the puzzle that helps us understand what is and what is not. The absence of evidence is not evidence of absence, as the saying goes, but it does help us narrow the field, focus our attention, refine our hypotheses. And there is another possibility, one that might seem disappointing at first, but that carries its own kind of wonder. Perhaps the gravitational evidence that led to the Planet 9 hypothesis can be explained in some other way, through mechanisms we have not yet considered, through interactions we do not yet understand. Perhaps the clustering of distant orbits is not caused by a single massive object, but by some more subtle effect, some property of the early solar system, or some influence from passing stars, or some aspect of gravitational dynamics that we have not fully appreciated. If this turns out to be the case, it would not diminish the value of the search. It would redirect our understanding, push us to think more carefully about the forces that shape the outer solar system, lead us down paths we might never have explored otherwise. The pursuit of Planet 9, even if it ends in the conclusion that no such planet exists, will have taught us things we could not have learned any other way. Spare a thought, too, for the trans-Neptunian objects themselves, those distant ice worlds whose strange orbits first hinted at the presence of something massive beyond Neptune. They are remarkable in their own right, these frozen wanderers at the edge of the solar system, each one a world unto itself, with its own history and its own secrets. Sedna, that reddish body with its impossibly elongated orbit, takes more than 11,000 years to complete a single journey around the Sun. For most of that time, it dwells in darkness so profound that the Sun appears as merely the brightest star in an endlessly black sky, a pale point of light offering no warmth, no comfort, only a gravitational tether to the distant heart of the solar system. What must it be like out there, in the realm where Sedna and its distant cousins travel? We can describe it in physical terms, can talk about temperatures that would freeze any gas we know, about darkness that has no earthly equivalent, about distances so vast that light itself takes hours to cross them. But there is something that escapes description, something that can only be felt through imagination, through the effort of projecting ourselves into that silent, frozen wilderness and trying to understand what it would mean to exist there. We are creatures of warmth and light, evolved on a world where the sun dominates the sky and drives all the processes of life. To imagine existence in a place where the sun is merely a distant memory, where warmth is a concept without meaning, where the only company is the slow wheeling of ancient stars, this requires a leap of imagination that pushes against the boundaries of what we can conceive. And yet these places exist. They are out there right now, as you listen to these words, tumbling slowly through the outer darkness, carrying their cargo of ice and rock and perhaps secrets we cannot imagine. They do not know we are searching for them, do not care whether we find them, do not experience the curiosity that drives our seeking. They simply are, existing in their own timeless way, indifferent to the brief flickering of human civilization on a small blue world closer to the sun, There is something humbling about this indifference, something that puts our concerns in perspective, something that reminds us how small we are against the scale of the cosmos. Return with me one more time to the question of what Planet 9 might actually be, to the possibilities that hang in the balance as the search continues. We have considered the three main candidates: the super-Earth, the rogue planet, the primordial black hole, but there may be other possibilities we have not yet imagined. The universe is fond of surprises, of revealing aspects of itself that no one predicted, of showing us that our models and theories, however sophisticated, capture only a fraction of reality. Perhaps Planet 9, if it exists, will turn out to be something we have not conceived, something that forces us to revise our understanding in ways we cannot anticipate. This is the true excitement of discovery, not the confirmation of what we expected, but the revelation of what we never imagined. Consider for a moment the history of planetary discovery. Each time we have found a new world, it has taught us something unexpected. Uranus, when it was discovered, seemed to misbehave gravitationally in ways that led to the prediction of Neptune. Neptune itself revealed the inadequacy of our understanding of the outer solar system, showed us that there was more out there than we had known. The discovery of Pluto opened our eyes to the Kuiper Belt, that vast ring of icy bodies beyond Neptune that we had not suspected, and the discovery of Eris and other dwarf planets forced us to reconsider what we mean by the word planet, to recognise that our categories are human constructions imposed on a cosmos that does not care about our classifications. Each discovery has been a door into a larger room, a glimpse of a universe more complex and more wonderful than we had imagined. If Planet 9 is found, it will almost certainly continue this pattern. Whatever it turns out to be, it will teach us something we did not know, will open questions we had not thought to ask, will push our understanding in directions we cannot predict. And if it is not found, if the search ultimately concludes that no massive object exists in the outer solar system, we will still have learned, still have grown, still have expanded our map of the possible. The journey is the reward, as the old saying goes, and the journey toward Planet 9 has already taken us to remarkable places. Let us sit for a long moment with the sheer improbability of our situation, with the strangeness of a species that can deduce the existence of an invisible world through mathematics alone. We are the universe becoming aware of itself, the matter of the cosmos arranged into forms that can contemplate their own origins, that can wonder about unseen objects at the edges of solar systems, that can build instruments capable of detecting the faintest gravitational whispers from the outer darkness. There is nothing ordinary about this, nothing that should be taken for granted. We are living in an age of wonder, an age when the tools of science allow us to perceive aspects of reality that would have been utterly invisible to our ancestors, aspects that remain invisible to our unaided senses even now. The mathematics that suggests Planet 9 exists is itself a kind of miracle, a language that humans invented to describe the patterns we perceive in nature, a language that turns out to be unreasonably effective at predicting things we have never seen. Equations scrawled on paper or typed into computers can describe the motions of objects billions of miles away, can predict where they will be centuries from now, can reveal the presence of things we cannot directly observe. This effectiveness of mathematics in describing the physical world is one of the deep mysteries of existence, a question that philosophers and scientists have pondered for generations without fully answering. Why should abstract symbols and relationships, products of the human mind, correspond so precisely to the behaviour of physical reality? We do not know, but we can be grateful that they do, can use this strange gift to reach beyond our immediate experience into realms we could never visit in person. Picture, if you can, the moment of discovery, if it ever comes. Perhaps it will happen late at night, in an observatory on a mountaintop, or in a computer lab where software is analysing the latest data from a sky survey. Perhaps a graduate student will notice something odd in the images, a point of light that has moved in a way that does not match any known object. Perhaps there will be hours of checking and rechecking, of ruling out artifacts and errors, of growing excitement tempered by caution. Perhaps the news will spread slowly at first, through emails and phone calls among colleagues, then faster as the confirmation becomes certain, then suddenly everywhere, headlines around the world announcing that a new world has been found. Or perhaps the discovery will happen differently, in a way we cannot imagine, in circumstances we cannot predict. The universe loves to surprise us, to deliver its revelations in unexpected forms. And we cannot leave this story without acknowledging the profound connection between the search for Planet 9 and the search for meaning that characterizes human existence. We look outward because we cannot help it, because something in us needs to understand the nature of reality, because the questions we ask about distant worlds are ultimately questions about ourselves. Why do we care whether there is another planet in our solar system? It makes no practical difference to our daily lives, will not help us grow food or cure diseases or resolve the conflicts that trouble our world. And yet we care intensely, invest enormous resources in the search, feel a deep excitement at the possibility of discovery. This caring is itself significant, a clue to what kind of creatures we are, what drives us, what gives our lives meaning. Perhaps the search for Planet 9 is really a search for connection, a way of feeling less alone in the vast darkness of space. Each object we discover, each world we add to our maps, makes the cosmos feel slightly more familiar, slightly more known. The outer solar system, once an uncharted void, has gradually become populated with icy bodies and dwarf planets, with objects we have named and tracked and studied. Each addition to this family makes us feel more at home in the universe, more connected to the vastness that surrounds us. Planet 9, if it exists, would be the largest addition yet, a world massive enough to make its presence felt across billions of miles of space, a companion we did not know we had. There is one more thing worth understanding about the nature of this search, something that speaks to the patience required for scientific work on the grander scales. The observations that might reveal Planet 9 take years to accumulate, require comparisons across long stretches of time, demand a kind of attention that is difficult to sustain in a world of instant gratification. An object as distant as Planet 9 would move so slowly against the background stars that detecting its motion might require observations separated by many months or even years. The astronomers who conduct this search are playing a long game, trusting that their patience will eventually be rewarded, accepting that the answer may not come within their professional lifetimes. This is a different relationship to time than most of us experience, a willingness to work on problems that may outlast us, to contribute to a project that began before we were born and may continue after we are gone. This long view connects the search for Planet 9 to the deepest traditions of astronomical observation, to the records kept by Babylonian skywatchers thousands of years ago, to the patient measurements of stellar positions by generations of astronomers who understood that their work would only bear fruit long after they had died. We are part of this tradition, inheritors of observations and methods and questions that stretch back millennia. The search for Planet 9 is the latest chapter in a very old story, the story of human beings looking up at the night sky and wondering what lies beyond the familiar lights, beyond the wandering planets, beyond the edge of the known. It is worth trying just once to feel the full weight of this continuity, to sense the hands of all those observers reaching toward us across the centuries, passing along their knowledge like a flame that must not go out. We stand at the leading edge of this tradition, benefiting from everything that came before, responsible for passing something forward to those who will come after. The search for Planet 9 is not just a scientific project, but a cultural inheritance, a question passed from generation to generation, each adding their piece to the puzzle, each expanding the map by some small increment. Whether or not we find Planet 9 in our lifetimes, we will leave behind better tools, better observations, better understanding for those who continue the search after us. And so, the darkness at the edge of the solar system continues to keep its secrets for now. Somewhere out there, perhaps, a massive world or a captured wanderer or an unimaginably ancient black hole pursues its slow orbit, indifferent to our searching, patient in a way that makes human patience seem like impatience. We will continue to look, continue to analyze, continue to hope. The question has been asked and we cannot unask it. The search has begun and we cannot abandon it. We are committed now, entangled with this mystery in a way that will not let us go until we have our answer, whatever that answer turns out to be. The night sky spreads above us, filled with stars that have burned for billions of years, and somewhere among them, or perhaps hidden in the darkness between them, the object we seek continues its ancient journey. We may find it tomorrow or next year or in a decade or never. We may discover that it was there all along, or that it never existed at all, or that what is there is something we never imagined. Whatever happens, the search will have changed us, will have taught us about ourselves and our place in the cosmos, will have reminded us that the universe still holds mysteries beyond our comprehension. And there is something wonderful about that, something that should make us grateful rather than frustrated, something that keeps the flame of curiosity burning even in the face of uncertainty. Let us sit for a long moment with that uncertainty and consider what it actually feels like to live inside a question that may never be answered. Because this is not a common experience in modern life, where most questions can be resolved with a few keystrokes, where the answer to almost anything is waiting patiently in the pocket of your hand. We have grown accustomed to knowing, to the satisfaction of curiosity fulfilled, to the closure that comes when the last piece of the puzzle clicks into place. But the search for Planet 9 offers no such guarantee. It asks us to sit with not knowing, to find meaning in the search itself rather than in its conclusion, to accept that some questions are valuable precisely because they resist easy answers. This is an old wisdom, one that philosophers and mystics have explored for millennia, but it takes on a particular flavour when applied to the cold mathematics of orbital mechanics and the patient work of astronomical observation. We are not wondering about the meaning of life or the nature of consciousness, questions that may be inherently unanswerable, but about a physical object that either exists or does not exist, that either orbits the sun in the darkness or does not. The frustration is that this question should be answerable, that in principle it is a simple matter of looking in the right place at the right time with the right instruments, and yet in practice it has proven maddeningly difficult. The cosmos is under no obligation to make itself easy to understand, and the solar system has turned out to be far larger, far darker, far more mysterious than we imagined when we thought we'd mapped its every corner. Return with me, one more time, to the moment of discovery, not a discovery that has happened, but one that might happen, that could happen tomorrow or next year or in 20 years. Imagine the astronomer at their computer screen, scrolling through the night's observations, comparing images taken hours or days apart, looking for that telltale shift against the background stars. They have done this thousands of times before, have seen thousands of false positives, have felt the momentary surge of excitement, followed by the familiar disappointment of another artifact, another glitch, another rock that was not what they were hoping for. But this time is different. This time the shift is real, consistent across multiple observations, moving in exactly the direction that the models predicted. The heart rate quickens, the hands tremble slightly over the keyboard, the mind races through all the possible explanations, all the ways this could still be a mistake. Colleagues are summoned, fresh eyes are brought to bear, the observations are checked and rechecked and checked again. Hours pass, then days, as the astronomical community collectively holds its breath, as the data is analysed and reanalysed, as the object is tracked across the sky, its motion traced backward and forward, its orbit calculated with increasing precision, and then, finally, the announcement, the moment when speculation becomes fact, when the hypothetical becomes the actual, when we learn at last what has been hiding at the edge of our solar system for billions of years. What would that moment feel like? What would it mean to know, after all this time, that there really is a ninth major planet, a massive world so distant that it takes 20,000 years to complete a single orbit? The joy would be immense, the satisfaction profound. But there would be something else too, something harder to name, a sense perhaps of the universe becoming slightly smaller, slightly more familiar, slightly less mysterious. A question that had animated decades of research would suddenly be answered, and while new questions would immediately spring up to take its place, there would be a kind of closure, a chapter ending, a story reaching its conclusion. Those who had devoted their careers to this search would feel vindication, and perhaps also a strange emptiness, the way an athlete might feel after winning the championship they had trained their whole life to achieve. What now? What next? What do you do when the dream you have pursued for so long finally becomes real? But there is another possibility, one we must consider with equal seriousness, and that is the possibility that there is nothing to find. Perhaps the orbital alignments that seem so suggestive are just coincidence, statistical flukes that tricked us into seeing patterns where none existed. Perhaps the gravitational anomalies have more mundane explanations that we simply have not thought of yet. Perhaps the solar system really does end where we thought it ended, with Neptune as the last major outpost before the vastness of interstellar space. This would be a different kind of discovery, a negative result that nonetheless teaches us something important about the cosmos and about ourselves. We would learn that our intuitions were wrong, that the universe did not arrange itself according to our expectations, that the darkness at the edge of the solar system is just darkness, empty and cold, and utterly devoid of hidden giants. This would be disappointing, certainly, but it would also be valuable, a reminder that the cosmos is not obligated to give us what we want, that science is as much about ruling out possibilities as it is about confirming them. We would know something we did not know before, even if what we learned was the absence of something rather than its presence. And then there is the strangest possibility of all, the one that keeps some astronomers awake at night and fires the imagination of others, the possibility that what we find is something we never expected, something that does not fit into any of our existing categories, something that forces us to rethink everything. We thought we knew about the formation of solar systems and the nature of cosmic objects. A primordial black hole would certainly qualify, an ancient relic from the very beginning of time, hiding in our cosmic backyard, warping space around it in ways we're only beginning to understand. But there might be other possibilities too, objects or phenomena that we have not yet imagined, discoveries that would make even the most speculative theories seem tame by comparison. The history of astronomy is filled with such surprises, moments when observers found something completely unexpected, something that had never appeared in any textbook or theoretical paper, something that expanded our understanding of the universe in ways no one could have predicted. Perhaps the search for Planet 9 will end with such a surprise, will reveal something so strange and wonderful that it changes the course of astronomical research for generations to come. Consider for a moment what it would mean if we discovered a primordial black hole in our own solar system. Such an object would be utterly unlike anything we have ever observed directly, a point of infinite density surrounded by a region of space from which nothing can escape. Not light, not matter, not even information. It would be small, perhaps no larger than a grapefruit, but it would contain the mass of several Earths, compressed into a volume so tiny that our normal intuitions about size and weight simply break down. To approach such an object would be to enter a realm where the laws of physics as we understand them begin to fail, where time itself bends and stretches and loops back on itself in ways that defy comprehension. We would have, in effect, a piece of the universe's infancy preserved in our midst, a fossil from an era so remote that even the oldest stars in our galaxy would seem young by comparison. The scientific implications would be staggering, but so would the philosophical ones. We would be forced to confront the fact that the universe is far stranger than we imagined, that even our own neighbourhood contains wonders beyond our understanding, that the darkness between the stars is not empty, but populated by objects we're only beginning to glimpse. It is worth pausing on what this would mean for our sense of place in the cosmos. We have grown comfortable with the idea that we understand our solar system, that we have catalogued its major components, that we know what lives in our immediate vicinity. The discovery of an object like a primordial black hole would shatter that comfort, would remind us that even the familiar can harbour the utterly alien. We would look up at the night sky with new eyes, knowing that somewhere out there, invisible and almost undetectable, a piece of the Big Bang itself was slowly orbiting the sun, a remnant of an era when the universe was hot and dense, and fundamentally different from the cold, empty vastness we see today. This would not be frightening exactly, but it would be humbling, a reminder of how much we do not know, of how much we may never know, of how vast and strange and wonderful the cosmos truly is. Picture, if you can, the darkness where this object might reside. It is not the familiar darkness of a moonless night, not the darkness of a deep cave or a shuttered room, but something far more profound, a darkness that has never known light, that exists so far from the sun that even the fiercest stellar glare is reduced to a dim spark barely brighter than any other star. In this darkness, the hypothetical Planet 9 or rogue planet or ancient black hole pursues its orbit, year after year after year, millennia stacking upon millennia like grains of sand accumulating in an hourglass so vast that human history is just a single grain. It knows nothing of us, of our searches and speculations, of our telescopes and algorithms and sleepless nights. It simply moves, responding to the gentle tug of the sun's gravity, following the path laid down by the initial conditions of its capture or formation billions of years ago. If it is a planet, it may have a surface, a landscape of frozen gases and ancient ice, mountains and valleys that have never been illuminated by anything other than the faint glow of distant stars. If it is a black hole, it has no surface at all, just a boundary beyond which our understanding fails, a door that opens in only one direction. Either way, it is patient in a way that makes geological time seem rushed, pursuing its orbit with a steadfastness that will outlast not just human civilization, but the sun itself. There is one more thing worth understanding, something that connects this cosmic mystery to our own lives in a way that might not be immediately obvious. The search for Planet 9 is, at its heart, a search for meaning, an attempt to make sense of patterns that we have observed but cannot explain. This is what human beings do, what we have always done, looking up at the night sky and trying to find order in the apparent chaos, trying to understand why things are the way they are. Our ancestors did this when they traced the paths of the wandering stars and gave them names, when they noticed that the seasons followed a predictable pattern and used that knowledge to plant their crops and plan their lives. We do it still, with more sophisticated tools and more rigorous methods, but the underlying impulse is the same, the desire to understand, to know, to find our place in the grand scheme of things. Planet 9 may or may not exist, but the search for it is undeniably real, a testament to the human spirit that refuses to stop asking questions, that cannot rest content with mysteries unsolved, that finds meaning in the pursuit of knowledge even when knowledge remains elusive. Spare a thought, too, for the generations who will inherit this question, if we cannot answer it in our lifetimes. Somewhere, perhaps, a child is being born tonight who will grow up to become an astronomer, who will spend their career searching the outer reaches of the solar system for signs of the hidden world that has eluded us for so long. They do not yet know that this question is waiting for them, that the mystery of Planet 9 will become their mystery, their obsession, their life's work. But the question will be there, passed along like an heirloom, like a responsibility, like a gift. They will use instruments we cannot imagine, will have access to data we cannot dream of, will bring fresh eyes and fresh ideas to a problem that has puzzled their predecessors for decades. Perhaps they will be the ones to finally answer the question, to point to a specific location in the sky and say, with confidence, that is where Planet 9 lives. Or perhaps they will pass the question along to yet another generation, adding their own contributions to the growing body of knowledge, their own observations and analyses and insights to the collective effort. Either way, the search will continue, driven by the same curiosity that has animated human beings since we first looked up at the stars and wondered what they were. Let us sit for a long moment with the strange beauty of this endeavour, with the image of human beings across generations working together on a single question, each contributing their piece to a puzzle that may take centuries to solve. This is one of the noblest things we do, one of the best expressions of what it means to be human, this willingness to work on problems that transcend our individual lifetimes, to contribute to a project that is bigger than any of us, to serve something greater than our immediate needs and desires. The search for Planet 9 is part of this tradition, connected to the builders of cathedrals that took centuries to complete, to the planters of trees whose shade they would never sit in, to all the countless human beings who did things not for themselves but for those who would come after. We are links in a chain that stretches back to the beginning of human civilization and forward to futures we can barely imagine. And there is something deeply moving about that, something that should make us feel both humble and proud. And so we come to the end of our journey tonight, though the journey itself is far from over. Somewhere out there, beyond the familiar planets, beyond the reach of our most powerful telescopes, something may be waiting to be discovered. It might be a massive ice giant, a world larger than Earth, but smaller than Neptune, shrouded in darkness and cold beyond anything we have experienced. It might be a rogue planet, a wanderer that once drifted between the stars, captured by our sun's gravity, and now bound forever to orbit a star it was never born around. It might be a primordial black hole, a remnant of the universe's earliest moments, ancient beyond comprehension, hiding in plain sight in our own cosmic backyard. Or it might be nothing at all, a mirage created by coincidence and wishful thinking, a pattern that seemed meaningful but was ultimately just noise. We do not know yet, and we may not know for many years to come, but we will keep searching, keep looking, keep asking the question that has haunted us since we first noticed the strange alignments of those distant objects beyond Neptune. The night sky spreads above you now, if you care to look, filled with the same stars that have guided human beings for countless generations. Most of what you see is ordinary, familiar, well understood, the product of centuries of careful observation and rigorous analysis. But scattered among those familiar lights are mysteries we have not yet solved, questions we have not yet answered, discoveries waiting to be made by those with the patience and the persistence to look closely enough. Planet 9, if it exists, is one of those mysteries hidden in the darkness, moving so slowly that its journey around the sun spans more time than human beings have existed as a species. It does not know we are looking for it, does not care whether we find it or not, simply continues on its ancient path, following the laws of physics that govern all things, large and small, near and far. But silence is not the same as absence. The darkness may be hiding something wonderful, something that will expand our understanding of the cosmos in ways we cannot predict, something that will remind us how much more there is to learn, how much further we have to go, how many questions remain unanswered. And even if there is nothing there, even if Planet 9 turns out to be a beautiful illusion, the search itself will have been worthwhile, will have taught us about the outer reaches of our solar system, will have refined our methods and sharpened our tools and deepened our understanding of the universe we inhabit. The questions we ask matter as much as the answers we find, and the question of Planet 9 has led us to places we never expected, has forced us to confront possibilities we never imagined, has reminded us that even our own solar system, the place we know best, can still surprise us. The night is quiet now, the stars steady in their places, and somewhere among them, or perhaps in the darkness between them, the object we seek continues its patient orbit. We are connected to it in a way, by the gravity that shapes all our motions, by the same laws of physics that govern both our breathing and its journey through the void. We are part of the same universe, subject to the same forces, made of the same atoms that were forged in the hearts of ancient stars. And perhaps that is the deepest lesson of the search for Planet 9, not whatever we find at the end, but the realization that we are bound to the cosmos in ways we are only beginning to understand, that even the most distant darkness is connected to us by invisible threads of gravity and history and shared origin. It is still out there tonight, whatever it is, pursuing its slow orbit through the cold and the dark, indifferent to our searching, patient in a way that makes human time seem like a breath. The search continues, the question remains open, and we are grateful for the mystery that has brought us here, to this quiet moment at the end of the day, contemplating wonders that exceed our understanding. We have the math, even if we do not yet have the image. We have the question, even if we do not yet have the answer. And we have each other, fellow travellers on this small planet, looking up together at a sky that still holds secrets we have not yet discovered. Thank you for travelling out to the very edge of everything with me tonight. The darkness there is vast, but it is not empty of wonder, and the search for what it hides is one of the great adventures of our time. Keep looking up, keep asking questions, keep marvelling at the mysteries that remain unsolved. Take good care of one another, and good night.